Hey everyone, and welcome back to This Explainer. Today, we're tossing out the dense jargon and classified data, and we're really just stripping things down to the raw, foundational mechanics of a seriously fascinating aerospace vehicle, the missile. We're going to build our understanding from the ground up, so let's just jump right into the pure, underlying science of flight.
Okay, let's dive into this. At its absolute core, before we get into any of the crazy advanced science, a missile is fundamentally just a vehicle trying to solve the problem of getting from point A to point B, traveling through the air toward a designated target. And I really want you to focus on that word, designated. Because, unlike an artillery shell that basically just follows a fixed ballistic arc the second it's fired, this vehicle operates in a highly dynamic environment, trying to reach a precise point miles and miles away, all while dealing with wind, weather, and extreme physical stress. That takes some incredibly complex engineering. Everything we're about to look at is essentially a technological solution designed to guarantee that specific journey through the air as a success.
All right, Section 1. What is a missile? Let's dissect the anatomy of this system piece by piece. To really unpack that, we have to start with a completely critical question. How does this vehicle actually begin its journey through the air? Just think about the sheer mass we're talking about here. You've got this object carrying a super dense payload, completely sophisticated electronics, and literally thousands of pounds of highly volatile aerospace fuel. Before aerodynamic flight can even become a thing, the very first massive engineering hurdle is simply overcoming an enormous gravitational penalty and the crazy inertia of all that weight. So how do we get this heavy, static object moving with enough brute force to eventually conquer the skies?
Which brings us to Section 2, generating the thrust.
So here is our first essential pillar of flight, propulsion. This acts as the foundational engine, generating the sheer thrust required to push the vehicle forward. But how does it actually do that? Well, whether it's using a solid rocket motor or some advanced jet turbine, propulsion really leans heavily on Newton's third law of motion. By igniting fuel, the system rapidly expands gases and just forcefully blasts them out the back. This really violent chemical reaction is what converts potential energy into massive kinetic energy, creating that pure forward thrust needed to push the whole thing upward. Without this sheer brute force mechanism, it's physically impossible to overcome gravity or kick off that high-velocity journey.
Okay, so we've solved the first big problem, right? The vehicle has harnessed that kinetic energy, it's officially off the ground, and it's establishing a high-velocity trajectory. But I want you to picture this vehicle in the air right now, propelled by all that raw, explosive energy. It's moving fast, sure, but is it actually stable? You quickly realize that raw thrust alone just isn't enough for a successful flight. I mean, propelling an object at Mach speeds through the atmosphere without any way to manage that immense kinetic energy, that is a recipe for absolute chaos, not precision.
Let's move on and see how this builds in Section 3, mastering the air.
You see, the atmosphere isn't just some empty void. It is a thick, dense fluid that pushes back incredibly aggressively against anything moving through it. And that's exactly where aerodynamics steps in to ensure efficient flight. When a vehicle blasts through the sky, it creates severe air resistance, which engineers call parasitic drag. And the crazy thing about physics is that drag scales exponentially with speed. So the faster this thing goes, the exponentially harder the air shoves back. Having a streamlined aerodynamic profile is what allows the vehicle to basically slice right through that resistance smoothly. This is absolutely crucial, not just to prevent catastrophic structural failure from the intense thermal stress, but to conserve all that precious fuel we just burned, effectively maximizing the vehicle's range.
But slipping efficiently through the air, that's really only half the battle. We also desperately need stability, and that is maintained by control surfaces. Any tiny atmospheric disturbance, like, say, a sudden wind shear or a quick pressure drop, could easily cause a fast-moving object to just tumble out of control by rapidly shifting its center of pressure. To counter that, engineers use specific physical components built right into the exterior. We're talking tail fins, canards up near the nose, or even thrust-vectoring nozzles right in the exhaust stream. These components are constantly interacting with that supersonic airflow, making these tiny micro-adjustments to keep the vehicle perfectly balanced and aerodynamically stable.
All right, so now we've got a vehicle equipped with the thrust to get moving, the aerodynamic profile to conserve energy, and the control surfaces to stay perfectly stable. But let's go back to our original definition for a second. It has to reach a designated target. What if that target moves? Or what if atmospheric conditions push the vehicle off its optimal trajectory? How does it actually adjust its flight path to ensure it gets exactly where it needs to go?
That takes us to Section 4, hitting the target.
Now, what's really interesting about this slide is that it provides a definitive solution to the incredibly complex problem of navigation.
Guidance systems provide the necessary intelligence, using advanced sensors and navigation tech to help the vehicle follow its intended path. Instead of flying blind on a fixed arc, these vehicles are packed with complex internal tech. Things like inertial measurement units, or IMUs, GPS receivers, and sometimes even highly sensitive optical or infrared seekers. These systems act like the brain of the vehicle, running continuous lightning-fast mathematical feedback loops. They constantly read the environment, calculate the exact distance and trajectory needed to intercept the target, and then fire off electronic commands to those control surfaces to steer the vehicle exactly where it needs to be in real time.
Finally, we come to Section 5, the aerospace engineering feat, where we bring all these micro-concepts back together into one unified system.
So we've looked at all these concepts individually, right? You've got propulsion for thrust, aerodynamics for efficiency, stability through your control surfaces, and guidance via advanced sensors. But the crucial point is that these are not isolated parts. For this vehicle to actually pull off its journey, these four distinct engineering pillars must operate as a fully integrated fly-by-wire system. They are entirely interdependent. Think about it. The guidance system relies entirely on the aerodynamics to physically execute its steering commands. The stability provided by those control surfaces, completely meaningless without the constant thrust maintaining supersonic airflow over them. If even one pillar fails, the whole system just collapses.
Successfully combining propulsion, aerodynamics, guidance, and control into a single, seamless vehicle is a profoundly demanding feat of aerospace engineering. We're talking about incredibly tight margins of error here. When you're flying at Mach speeds, a fraction of a degree in control surface deflection or just a millisecond delay in a guidance calculation can literally mean entirely missing a target or, worse, causing catastrophic structural failure. Mastering these physical laws so they all work in this beautiful, continuous harmony is really what elevates this from just a simple moving object into a true marvel of modern engineering design.
To wrap things up, I want to leave you with a final provocative thought to chew on. What other everyday vehicles rely on these exact same four pillars of flight? Think about the commercial jetliners you fly in for vacation, or the space rockets launching our cell service satellites into orbit. They actually all share this identical, fundamental engineering DNA. Thank you so much for joining me on this explainer today. I really hope that the next time you look up and see a vehicle soaring through the sky, you'll view it just a little bit differently, fully recognizing the universal mechanics of flight working together to keep it aloft. Keep learning, and I'll see you next time.